Good morning, everyone. I welcome you all to this lecture. In this lecture, we are going to discuss a very important topic in automata theory, that is minimization of DFA, deterministic finite automata. We can minimize a given deterministic finite automata by following certain number of steps. Okay? And when we are designing a machine, we must be intended to design a minimized state machine where it should have minimum number of states, so that implementation and the execution or computation power should be utilized less, right? So let's look at the state. Remember one thing, when we want to minimize an automata, that automata must be DFA. We should not try to start minimizing the non-deterministic finite automata, right? So that is one thing you should remember. Now when you want to minimize an automata, you need to follow these steps. So the very first step, you consider, first we need to understand the automata. What are the number of states, the tuples, the transition, and number of other things are there. So we do understand, and we know that there are 5 tuples in automata. So set of states, set of alphabets, transition function, initial and final states, right? So we do understand the automata first. Then we start grouping these states. So we assume that whatever the automata is given, and let's say we are going to minimize it, so I assume that finally there will be 2 states only, one as initial state, one as final state. So what we do in the very beginning or first step, we prepare a group of non final states and final state, by believing that possibly finally there will be 2 states only when we minimize the given automata. Okay, so we prepare 2 sets. Okay, one, they are saying the accepting state or final state, that is F, and another Q minus F. Q is the total state, minus F the remaining state, right? Those are non-final. Then in third step, we start doing the iterative partitioning. So whatever the groups we have created, based on the equivalence, we try to check whether the states will be in the same set or different set, and then we do further partitioning of the given sets, right? So how do we do that? We see, based on the equivalence, 0 equivalence, 2 equivalence, and so on, there are classes, and if the final states will belong to the same sets, then these states will be there, otherwise it will be partitioned. So we will see later on. The third step is the iterative partitioning, which we are going to see in the next example. Forming the new DFA. So once we have done all the partitioning has been saturated, so we initially has created the set of non-final state and final state, then we start partitioning of those based on some logic which we are going to see in the example, and then finally we start getting the same partition set. Then we start framing the automata. Now when we start framing the automata, then we decide what are the accepting states will be there as per the combination of final states which we get finally in the group. And then if there are any unreachable state, if you find out any unreachable, we remove that. Okay, and after doing that, the finally automata we will construct. So this process of automata minimization may be very cumbersome, very tedious. So here I have highlighted the automata minimization can be computationally very intensive. That means it may require high computational power. So there are certain well-known algorithms available, like Hopcroft's algorithm and Moore's algorithm. So these two name you can remember, because these algorithm, neither it has been asked in the GATE or the UGC net, but indirectly we use these algorithms to minimize the automata. So you can remember the name. Okay. Now let's discuss one example, which is I am taking very easy example of automata minimization. So the very first step when we start preparing the groups. So if I prepare the groups for this, I prepare one non-final state and another group of final state. So non-final states here are like Q1, Q0 is the non-final, Q1 is also a non-final, Q2 is also a non-final, and Q3 is also non-final. So one set we are preparing like this. Another set there is only Q4, because Q4 is the final state. So this is the very first step in which we are grouping these states. We create two groups, non-final and final. Now what we check later on, so we believe that all these states will be in zero equivalence. Zero equivalence means when we are at a state and we do not pass any input, zero length input or epsilon input, we will be on that state only, right? And if that state is non-final, that means all non-final states is in equivalence because they are leading towards non-final without taking any input, and all final states will be in zero equivalence because they are leading us to final only without taking any input. So that is the logic. So this is we consider zero equivalence class. So sometimes we represent in some of the books like pi zero equivalence classes. In the very first step we write the zero equivalence class. Now in next step we start partitioning this. So we try to get one equivalence class. One equivalence means when we pass one length input on any of these states, whether they belong to the same set or different set. So how do we find out? Let's check it. On Q0, so we start forming the group, let's say Q0. And Q1, we are deciding whether Q0 and Q1 will belong in the same set or not. So let's pass one length input. On Q0, when 0 is coming, it is on Q2. Q2 is in this set and that is non-final, right? And on Q0, when 1 is coming, it is on Q1. Q1 also belong in the same set. Now look at the Q1. Q1, when it is taking 0, it is on Q2, that is in the same set. But for 1, it is leading you to Q4. But Q4 is not in the same set. It is belonging in another set, and that is the final state. So that means it reflects that Q0 and Q1 cannot belong to the same set. So I create another set. Q1 must be belonging to the some other set. Okay. And Q4 is finally there because Q4 is having only one state. So that will be there. It will not be further partitioned. Right? If you decide Q0 and Q2, same thing we need to check for Q2. So this Q2, Q3, they are belonging in the same set. So that is also fine. Q3, it is Q2, Q4. It will also belong in this particular set because Q2 is non-final and Q4 is final. So it will not belong in the set with Q0. So that is Q3, right? So Q2 is belonging in the same set. So I can write Q2 here because Q2 is having for both, it is having non-final transition. So it will have in this. In one equivalence, it will be with Q0. Now for what is Q4? Q4 is there. So there are total 5 states. So the sets will look like this. Okay. Now if you try to find out the two equivalence, that means when we pass two length input, what will be the resultant state? Whether for 0, your state will lead to final state or non-final state. Based on that, we claim two equivalence. So let's check for Q0, Q2. Now Q0 lead you Q2 and Q1. Q2 is belonging in this set and Q1 is belonging in another set. Now let's check for Q2. Q2 is leading you Q2 and Q3. So Q2 is belonging in this and Q3 is belonging in this. That means same set it is leading for 0 and same set it is leading for 1, right? So for Q2 again I highlight Q2 is leading you to Q2 for 0. Q2 is available here, right? And Q2 is leading on Q3. So Q3 is available here, right? So in this set and in this set for 0, both Q0 and Q2 are leading you towards here, and for 1 both these this Q0 and Q2 is leading you towards this set. That means there is no further partitioning required. So this Q0 and Q2 will belong to the same set, right? Now let's check for Q1, Q3 whether it can be partitioned further. So let's check for Q1. Q1 is leading us to Q2, Q4. So Q2 is in this set and Q4 is in this set, right? Now let's check for Q3. Q3 is leading us to Q2, Q4. So same, Q2 is here and Q4 is here, that means same set. So Q1 and Q3 will also belong to the same set. It is in pi 2 equivalence also, or 2 equivalence class they belong. And Q4 obviously there is single state, so it cannot be further partitioned. So that means once we start getting the same, because in steps we see that once we get no further partitioning is possible, we get the same set from the previous state to the new one, previous equivalence class to the new equivalence class, then we saturate the thing and we start drawing the automata. So that means final automata will have only 3 states. So let's say this state I named as, let's say this is A, this is B, and this is C, and C will be your final state. So the combination of these two states I am defining as single. Okay, initial will be which set, wherever initial state is existing. So this A state will become the initial one. So let's say I am drawing the automata. A is my initial state, which is the combination of Q0 and Q2, and B is another state which is non-final, and Q4, let's say I'm drawing here, Q4 means C, so C is here and that is the final state, right? So we can write the transactions. So how do we decide the transaction? From, let's say, this initial state when 0 is coming. So on Q0 when 0 is coming, it is leading you Q2. Q2 is in the same set. That means there will be a loop. There will be a loop for 0. Okay. Because another state is also leading you to the same set. Right. And for Q0, you are leading to Q1 and Q1 belongs in this set. So that means there will be a transaction from A to B here for 1, right? Now look at for B. B, just we need to check 1 and remaining thing will be same because the set are created like that. So Q1 is leading to Q2, Q4. So that means Q2 is the same, Q2 belongs in this set. So we are coming back to this for 0. Okay, and from here we are going to Q4. So Q4 is the final one, like C state. So we are reaching by traversing 1 here. Now let's write the transactions for C. C means Q4. Q4 is having self loop for both 0 as well as 1. Okay, so this automata, which was initially having 5 states, after minimization it will have only 3 states. Okay, so I hope the minimization of automata is clear. In further or next lecture I will take few more examples to clarify you. So this is very easy process, but it is very important process. Okay, so we have already seen NFA to DFA conversion, null NFA to NFA conversion, right? So I'm closing this lecture. See you in the next class. Thank you. Happy learning.